Hello class, in this video I will go over the same experiments, the last experiments that we studied that involve the concept of independent events. Basically, we already solved them all, I believe, except this one, the experiment number 3. But basically, even though we have already done them, I want to go over each one of them in order to explain them quickly to you, because in class, basically I was waiting for you to answer some of these questions, etc. And here, it's basically going to be everything uh, rather straightforward. So let's start, guys. Let's analyze this experiment number 1, which is throwing a fair coin and a fair die at once. And let's define the events A and the event B. The event A is getting heads on the coin, and the event B is getting the number 3 on the die. And they're asking us whether A and B are independent events. Okay, remember, in order to make sure that two events are independent, we have to have a rather compelling argument. It has to be very straightforward. If that's not the case, you cannot assume independency. So in this case, you have a coin and a die, and they're being thrown independently, right? Like there's no possible connection between the motion of the coin and the motion of the die. In such a case, it is very straightforward to assume independency. So are A and B independent events? Yes. And let's do some other things in here. Just to confirm, right? We already know that they are independent. We have already established that. Give me a moment because this thing is not okay. There it is. No, it's not working. Just give me a moment. Let me pause the video so I can get this thing working. Okay, so now it is working perfectly. So are A and B independent events? Yes, because it's very straightforward to see that they are independent events. Let's calculate the probability of A, the probability of getting heads on the coin. How many favorable? Remember that the formula for probability is the number of favorable outcomes to the event A over the number of all possible cases in the sample space. This is the sample space. It contains 12 outcomes, singular outcomes, and let's see which ones of them are favorable to the event A, getting heads on the coin. It's all of these 6, right? So we have 6 favorable events. 6 favorable outcomes for the event A out of 12 possible outcomes. So we have 1/2. The probability of A is 1/2. The probability of B getting a 3 on the die, only this one and this one are favorable outcomes. And so that's 2 favorable outcomes over 12 possible cases, and that's going to be 1/6. And as you can see, these probabilities, 1/2 and 1/6, is pretty much the independent probabilities of each of these experiments if they were done independently from each other. You see, like if you throw a coin, you know that getting heads will have a probability of 1/2, and if you throw a die alone, you know that the probability of getting 3 is 1/6. Okay, so we have the probability of A and we have the probability of B. Now let's calculate the probability of both of them occurring at the same time, getting heads on the coin and getting a 3 on the die. So when looking at this event A and B, basically the only outcome that represents this event or that is favorable to this event is this one, right? Getting heads on the coin and getting a 3 on the die. So it's one favorable outcome over 12 possible cases, so the probability of this event is 1/12. Okay, so we have the probability of A, the probability of B, and the probability of A and B. And we already knew that the events A and B were independent, because it's very straightforward to see that in such experiment. Now let's see if the formula works. Remember, this formula, the formula for the probability of A and B is equal to the multiplication of the probabilities of each of these events independently, only in the case of independent events, when you know that A and B are independent. So let's see if it actually checks with this experiment. What is this? 1/12. What is P of A? That's 1/2 times P of B, which is 1/6. So of course this equation checks, as we knew it. You see? So that's pretty much the experiment number 1. Very simple experiment. Let's see the experiment number 2. In this one, we have the same experiment basically under 2 different variations. So in this case, we have a bag with 6 balls in each of the variations. In each of the variations, we have 3 striped balls and 3 solid ones of solid color. And the experiment is about choosing 2 balls, one after the other, with replacement. In the case of the variation 1, we want to replace the first ball. Once we have the bag and once we take out the first ball, we're going to put it back again, and then we're going to take out the second ball. That's how this variation works. When you draw the first ball, you're going to put it back, and then you're going to take out the second ball. Okay, in this case, let's define the event A and the event B, getting a stripe in the first ball and getting a stripe in the second ball. So what's the probability of A? Well, there are 3 stripe and 3 solid. So we know that we have 3 6, right? Because there are 6 balls. So it's basically 1/2. And the probability of B, for this case also, the probability of getting a stripe in the second ball will be the same as getting a stripe in the first ball. It's going to be 3/6 or 1/2. Why? Because remember that the first ball was returned to the bag. So basically the sample space for the event B is the same as for the event A. You see, basically the whole experiment returns to the original position once you get the first ball inside. So both probabilities are the same. Okay, and how can we assert whether A and B are independent events? Well, just ask yourself, if A happens or doesn't happen, does that affect the probability of event B? And the answer is no. No, it doesn't. Okay, the probability of B will still be 1/2 whether A has occurred or not. And that is basically the test on how you can check for independency. Well, that's one of the tests. Okay, now in the second variation, we perform the same experiment. The only difference is that we are not going to replace the first ball when we draw it. So you have the bag, you're going to take out the first ball, and you're going to leave it outside. Okay, you're going to keep it there, and then you're going to take out a second ball. So in here the problem is, guys, that once you have taken the ball number 1 and once you leave it outside, that already changes the configuration of the experiment for the drawing out of the second ball, and that's going to change the experiment, right? So let's see. In this case, what is the probability of event A, getting a stripe in the first ball? Well, as before, that's going to be 3 favorable cases over 6, which is going to be 1/2. And now, what is the probability of event B? Well, once I have drawn the first ball, now in my bag there are only 2. Let me actually draw them in this way. We have 2 stripe and 3 solid color. Okay, once I have taken the first ball and assuming it's a stripe, then the sample space is gonna look like this, right? I mean the whole configuration of the experiment is gonna look like this. Once I take out of the first ball and assuming it's a stripe. Now assuming it's solid in the first ball, then I would have something like this: stripe, 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 and then solid, and then solid. You see, in this case, A happens, and in this case, A did not happen. So, assuming this case, in the case that event A happens, then the probability of B is going to be 2 favorable outcomes out of 5. So that's the probability of B, assuming A happens. And assuming A doesn't happen, then the probability of B, which is getting a stripe in the second ball, will be 3 favorable outcomes over 5 possible ones. So that's it. In the first case, the probability of B is 2/5, and in the second case, the probability of B is 3/5. What can we observe? Well, what we can observe is that whether A happens or doesn't happen does affect the probability of B. It does affect it. It has an effect on this probability, and therefore we should answer this question as no. A and B are not independent, because when A happens or doesn't happen, then that changes the probability of the event B. Okay, so that's how you solve this problem for the experiment number 2. Now let's continue with this experiment number 3. This one we didn't do it in the class, so let's take a look at it. This is just basically a rather qualitative experiment. We're not going to do any mathematics. We're just going to answer these 2 questions with words, with very simple reasoning. So what is the experiment? The experiment is choosing one person at random from the region below, from this green region, which comprises Mexico and the United States. And after we have chosen this person, we're going to observe, we're going to write down the sex, male or female, the nationality, American or Mexican. I'm going to represent Mexican with an X, and the most fluent language of this person, which could be either English or Spanish. And then I'm given this remark: consider sensible assumptions. Es decir, consideremos cosas sensatas. Podemos asumir cosas o hechos sensatos. Okay, so let's define these 3 events: A, B, and C. The event A is the person chosen is female. The event B, the person chosen is an American. And the event C, the person chosen is a Spanish speaker. This is the sample space. I can get all of these 8 outcomes. Try to look at this. You can pause the video for a moment and try to understand each of these outcomes. Okay, and try and realize that not all of them are equally likely. For example, this one, having a male American that speaks English, is much more likely than having something like this, right? A male American that speaks Spanish. We get the idea, right? So they're not all equally likely. So let's answer the questions, guys. First question is this: are A and B independent? Are A and B independent? How can I know that? Well, ask yourself, if the event A happens, or it doesn't happen, does that change the probability of the event B? That is a question that you have to ask yourself. Okay. For example, if I know that the person chosen is female, does that give me any reason to think that it is more probable that the event B happens? It is more probable that the person will be American or not? That is a question. And by considering sensible assumptions, we can say that no, they're not in, I'm sorry. Yes, they are independent. Yes. Why? Because whether A happens or not doesn't affect the probability of B. Okay, if I know that the person that I choose from this section is a female, that doesn't let me know whether there is a higher chance that this person will be American or Mexican, right? Why can I say this, guys? Why can I answer this question in the positive? Because I told you, let's consider sensible assumptions. And a very sensible assumption is to think or to realize that the ratio of male to female are the same in both countries. You see? So basically, if I know that I have chosen a female, that already, I mean, that doesn't affect the possibility or the chance of this being American or female or Mexican, right? So yes, they are independent. A and B are fully independent. Now, on the other hand, are B and C independent? So let's take a look at B. B is the person chosen is American. So suppose that the person that you chose out of this region is American. Does that, if I already know that this happens, that the person that I chose was American, does that make the probability of event C higher or greater? Does it affect the probability? Yes, right? It's gonna pretty much decrease the probability of event C. If I know that the person chosen is American, then I know that the probability of the event C will be reduced, right? Why? Because in the United States, there are less people that speak Spanish than people that speak English. You see? So, are B and C independent? No. No. They are dependent. Because if B happens, that's going to affect the probability of event C. Okay? So that's basically all I wanted to say about this particular experiments. Just some comments on these questions. Now on to experiment number 4, which is this. We're gonna roll a fair coin and a fair die and register the possible outcomes. So as before, there are 12 outcomes for this particular experiment, and here they are listed. Now let's define these two events. The event A, the coin coming up head, and the event B, the die coming up an odd number. Are A and B independent or dependent events? So once again, guys, in here, there is no connection. There is no possible connection between event A and the event B, right? So we know that they must be independent. They must be independent events. So let's calculate the probability of A and B. This is the first thing I want to find out. The probability of A and B. How can I calculate that? Once I know that they are independent events, well, that's going to be the multiplication of the individual probabilities. And so basically all I need to know is this number, P of A, and this number, P of B. So let's see. What is the probability of event A? The coin coming up heads. That's going to be 1/2. Make sure of that. You can pause the video and make sure about that. And what is the probability of event B? The die coming up an odd number. That's once again 1/2. Just count the possible outcomes that are favorable to B and divide over the possibilities, and you will have 1/2. So that's it, guys. Basically, the probability of A and B is going to be equal to 1/2 times 1/2, which is 1/4. That's it. And next, calculate the probability of A or B. So the probability of A or B, remember we have our table of formulas. I haven't given you this table though, I think, but I'm gonna do it in a moment. This table right here for disjoint events and for joint events. We have the probabilities of A or B, A and B for both cases. So in this case, since we have these two events, remember that we can basically consider these two formulas as the same, right? These two formulas are pretty much the same, because basically if I'm telling you that for these joint events the probability of A and B is 0, then it wouldn't matter if I wrote the following here. That would not make any difference. I wrote this. That wouldn't make any difference. Why? Because once again, for these joint events, this probability is 0, and when you put that 0 in here, basically you get the reduced version, which is this. You see? So basically we can consider this as the general universal formula, whether we're talking about these joint events or joint events. This is the general formula for A or B. So let's actually copy it and bring it to our problem. So the probability of A or B, that's going to be equal to the probability of A plus the probability of B minus the probability of A and B. Do we know this? Yes, it's 1/2, right? We know this. It's 1/2. And we also know this because we already have it from the previous analysis. Minus 1/4. And so basically that leads me to say that the probability of A or B, I'm sorry, I got confused here. Probability of A or B is going to be equal to 1 minus 1/4, which is 3/4. So there you go. This is the probability of A or B, 3/4, and this is the probability of A and B, 1/4. And that solves the experiment number 4. So now experiment number 5. We have the rolling of 2 fair dice. Okay, so this is the sample space. As we know, we have been doing this sort of experiment already a few times, so you know that this is going to be the sample space. It's going to contain 36 possible individual outcomes. And let's define the event A. Give me a few seconds. I was saying the event A is that the first die comes up an odd number, and the event B, the sum of both dice is 4. In this experiment, guys, if you remember, it was a little tricky, a little difficult to say from the start in an a priori way whether these two events are independent or not, whether they are in some way connected. Okay, and remember, when you don't feel very sure about the independency of two events, don't assume it. Don't assume it. Okay, so at this moment, we don't know. This question will be kept, let's say, unsolved at this moment. That doesn't mean, you need to understand this. I'm just refusing to answer this question. You see, I don't know if they are independent at this point. That doesn't mean that I know that they are dependent. You see, I'm basically refraining from answering this question at this point. And let's take another method in order to solve these two questions. Calculate the probability of A and B. So I'm being asked to calculate the probability of A and B. Once again, since I'm not sure that A and B are independent, it would be a mistake to right away write this formula and then look for this, multiply them, and getting this probability. That would be incorrect. Why? Because at this point we don't know whether they are independent or not. So don't use it. Don't use this formula for solving the first question. What other route can we take? Well, the most simplistic method, which is just basically counting all the outcomes that are favorable to this event, the event A and B, or the event in which both of them happen. So, for which outcomes of this are both A and B occurring? For which of these events? So, let's see. The event A happens for all of the following outcomes. All of this column, can you see? Because the first die, well, let me actually, now I was making that mistake. I'm sorry, it's this row, and this row, and this row. For all of these outcomes, guys, the first die is coming up odd. Can you see? This is the first die, 1, 1, 1, 1, and then 3, and then 5. For all of these outcomes, we have that the event A happens. And which outcomes account for B? The sum of both dice is 4. For this one, and for this one. You see? So, once again, the question, for what outcomes do we know that A and B are happening? Well, only for this one. Can you see? I'm going to put them in blue. For this event and for this event, both A and B are happening at the same time. The first die is an odd number, 3 and 1, and the sum of both dice is 4. 3 plus 1, 4, 1 plus 3, 4. So only two outcomes are favorable to this particular event. So it's 2 over how many possible outcomes? 36. And let's reduce this fraction to get 1/18. So we have already solved this question without making reference to any formula or anything complicated, just by counting the possible outcomes. All right. So question 1 is solved. Now, calculate the probability of A or B. Okay, we can do that in a moment. We can do this in a moment. First, I'd like to know whether we can already answer this question. Are A and B independent? Well, remember, at this point we don't know. We only have this piece of information. And now let's actually get the probability of A and the probability of B independently. I'm gonna leave that to you. It's very quick. It's very simple. Pause the video. And then you're gonna notice that the first die coming up an odd number has a probability of 1/2. And the sum of both dice is 4, has a probability of 3 over 36, which is equal to 1/12. Okay, so these are the individual probabilities. Now, once I have the probability of A, the probability of B, and the probability of A and B, we can actually check analytically through a test whether A and B are independent. And that test is actually the formula. I'm going to write down the formula, this one. And if I notice that this is equal to the multiplication of this times this, then that's because they were independent to start with. A and B were independent. So let's see, the probability of A and B is 1/18. The probability of A is 1/2. And the probability of B is 1/12. So clearly, this and this multiplication are not the same. So this equation is not satisfied, right? And what that leads me to say is that A and B are not independent. They are not independent. So that's how you can check for independency, guys. Once you have the individual probabilities of the two events and also the probability of both of them happening at the same time. Once you have all of those three things, then you can use the formula as a test for independency. And in this case, they were not independent. Okay. And now let's solve the last question. Let's clean this up. The last question was calculate the probability. Well, let me erase the whole thing. Calculate the probability of A or B. Remember, the probability of A or B is the probability of A plus the probability of B minus the probability of A and B. So this is going to be probability of A, it's going to be 1/2. The probability of B is going to be 1/12, and the probability of the event A and B is 1/18. And that's it, guys. This is it. You can actually leave it like this if you want. Doesn't make any difference. That's the solution. So that concludes the experiment number 5. Now in experiment number 6, we're gonna suppose that we have a classroom at CDEP and there are 2 smoke detectors, 1 and 2. Each one of them has a reliability of 90%, which means that they can detect smoke 9 out of 10 times. And let's assume there's a smoke in the classroom, in this classroom right now. Fine, that is the whole context. Now, let's define the event A, that the smoke will be detected. And we want to calculate the probability of A. So let's see, guys. Remember what I told you in class. In many cases, what you need to do is rephrase or restate or change the interpretation of event A into something that you already know. For example, what do you know at this point from the context of the problem? You know the probability that each of these detectors will detect smoke. And if I do the following, if I define 2 events, I'm going to call them D1 and D2. I say, okay, I'm going to define these 2 events. The event D1 is that the detector 1 detects smoke. And D2 is going to be the event defined as the detector 2 detects smoke. Then I already know the probabilities of both D1 and D2. The probability of D1 is going to be 9/10, and also the probability of D2. Okay, so can I reinterpret the event A somehow using the events D1 and D2? And the answer is yes. Basically, we can see that the smoke will be detected. In other words, A will happen if either D1 or D2 happens. Let's write that down. A is equivalent to D1 or D2. What is A? The smoke, the event in which the smoke will be detected. That's equivalent to whether D1 or D2 happen. You see? And so if I want to find the probability of A, that's going to be the same as the probability of D1 or D2. That's how you rephrase an event into some other two as a composition of events or a combination of events for which you already have the probabilities for each of these. You see? Okay, so now let's actually try to solve this task. What is the probability of D1 or D2? Well, let's do it here. The probability of D1 or D2 is, by the formula, the probability of D1 plus the probability of D2. Give me a moment. Sorry about that. Okay, I'm back, guys. Okay, we were writing this formula, right? And then minus the probability of D1 and D2. Okay, so if I want to know this, I must know this and this and this independently. So I already know this and this. So let's write them down. 9/10 plus 9/10 minus the probability of D1 and D2, which I can get rather quickly through means of the formula, right? Through means of this formula. If I know that D1 and D2 are independent only if D1 and D2 are independent. So if I know that they are independent, I can use this formula. Do we know that? Do we know that D1 and D2 are independent? What is D1? The event in which the detector 1 detects smoke, and D2 is the event in which the detector 2 detects smoke. They are completely independent, guys. Why? Because given the context of the problem, given the situation that we are analyzing, we can see that, the smoke will be basically filling the whole classroom, right? And it will be getting into the detectors, and they're working independently, right? Whether this detector activates or not, that doesn't matter to the probability of the other one to also detect the smoke. You see, they are completely independent systems. So yes, in this case, it's reasonable, very reasonable, to assume independency of D1 and D2, and therefore I can go on in the usage of this formula. So let's use it. This is going to be the multiplication of the probability of D1, which is 9/10, times the probability of D2, which is also 9/10. And that's basically the solution. This is my solution. It can be written like this, there is no problem. Although if you actually calculate the whole thing, you're gonna get 0.99. Yeah, I think that was the. Let me just check very quickly, but I think that was what we got the other day. Yes, it's 0.99. So this is the result, right? And now we just go back to our event, our original event. You must understand that the author of this problem is not asking you about the probability of D1 or D2, because in the first place, the author of this problem does not even know what D1 and D2 are. You define these two events in order to help yourself solve the problem. So what is the solution that you should give? Well, that the probability of A, which is the same as this, right? A is equal to this. That's going to be equal to 0.99. So the probability of A is 99%. And that solves this experiment number 6. And finally, let's go through experiment number 7. This is a new one, which is a slight variation on the previous one. A slightly more complex variation. It's pretty much the same, you will see. So in this problem we have the following, guys. We have go back here. We have the following. Trained dogs are used to detect bombs at airport checkpoints. Suppose you have two of these dogs working at a checkpoint. Okay, and let's keep on reading. Through experimentation, it has been observed that the dog 1 has a probability of 0.99 to detect a bomb inside a suitcase, and dog 2 has a probability of 0.95 of detecting a bomb inside a suitcase. So in this case, both dogs, let's dog 1 is slightly better at its job than dog 2, right? That's basically what it says. Okay, now let's assume that two suitcases, each containing a bomb, are in the checkpoint waiting to be packed into a flight. Each suitcase is given to each dog to sniff. Okay, that is the whole context. And then the question is the following. What is the probability that the airport security will detect both bombs and make the flight safe? Okay, so that is the whole problem. If you want to stop the video and read the whole thing once or twice again, do it, because I want you to understand the whole context of the problem and the question. Okay, so let's see, guys. They want me to find the probability that the flight will be safe. So let me define that event. I'm gonna call it S for safe. Okay. You know, the events don't always have to be called A and B. Actually, it's better to give them meaningful names. In this case, S is the event that the flight will be safe. Okay, now how can I interpret this in terms of other events? Just like before, how can I reinterpret or rephrase this event? Well, I can create two other events, B1 and B2. And the event B1 for me will be that the bomb 1 is detected, and B2 is the event of the bomb 2 being detected. Okay, so how can I interpret S in terms of B1 and B2? Well, S is going to be equivalent to B1 and B2, right? It has to be and. Why? Because the plane will only be safe when both bomb 1 and both bomb 2, bomb 1 and bomb 2 are detected. So both of these events have to happen in order to make the flight safe. So we can see that this is equivalent to this. And if I want to calculate the probability that the flight will be safe, then that's going to be equal to the probability of B1 and B2. Okay, so this is the first equation I can come up with. Perfect. Now, how can I find the probability of B1 and the probability of B2? How can I find these two things? The probability of B1 and, well, give me a moment, and the probability of B2. Can I find them? Can I also rephrase each of these events in terms of other events for which I know the probabilities of? Yes, we can. And I can also interpret these two events as a combination of even further events. What events? If I'm gonna write it here, event D1, which is that the dog 1 detects a bomb in a suitcase, and D2 is the event in which the dog 2 does the same for the particular suitcase. So I'm not going to write this thing. So D1 is basically this, the probability that when you give a suitcase with a bomb to a dog to sniff, the dog will detect the bomb inside the suitcase. That's D1. And D2 is the same for the dog 2. Basically the same. So how can I reinterpret B1 in terms of D1 and D2? Well, the probability that the bomb 1 will be detected is basically, if you notice, is basically the probability is going to be equal to the probability of either dog 1 or dog 2 detecting the first bomb. You see, so in this case it's going to be an or. The probability that the bomb 1 is detected is equal to the probability that the dog 1 detects such bomb when it's given it to sniff, or that the dog 2 will detect such bomb. Because remember, each of these suitcases, for example, let's suppose that this is the first suitcase with a bomb. It will be given to the first dog to sniff, and then it will be given to the second dog to sniff also. You see? So we can agree on this, right? And the same is going to be for the bomb 2. The probability that the bomb 2 will be detected is going to be equal to the probability that the dog 1 detects it, or that the dog 2 detects it. You see? Okay, perfect. Now, are we ready to investigate these probabilities? Yes, because we do know the probability D1 and the probability of D2. Those are the probabilities that we were given at the beginning. The probability D1 is 0.99. That's the probability that the dog 1 will detect a bomb in a suitcase. And the probability of D2 is going to be equal to 0.95. Perfect. So we can already calculate this probability and this probability. I mean, basically they are the same, right? So the probability of D1 or D2 is by definition, or I mean by formula, the probability of D1 plus the probability of D2 minus the probability of D1 and D2, right? Okay, so do we know the probability of D1 is 0.99. I'm gonna erase this for the moment, guys. So this is gonna be 0.99 plus the probability of D2, which is 0.95, minus the probability of D1 and D2. Now at this point is where again we think of the independency and D1 and D2 of these two events. Are they independent events? Are D1 and D2 independent events? D1 is the dog 1 detecting the bomb in the suitcase given to him, and D2 is the event in which the dog 2 detects the bomb in the suitcase given to him. Okay, clearly, once again, these are independent events. Okay, whether this dog detects the bomb in here, in this suitcase, when you give the suitcase to this other dog, it's not gonna matter whether the first dog has already detected the bomb inside it or not. This dog, I'm sorry, works independently from this one, and so we can assume once again independency of events. So D1 and D2 are independent, and therefore I can establish this, or well, I can find the probability of D1 and D2 simply by means of the multiplications of the probabilities. So that's gonna be 0.99 times 0.95. Okay, and we have all of these expressions which we can calculate. Let's do it. And what I get is 0.995. That is the probability of B1. What is B1 again? It is the probability of the bomb 1 being detected. It's this much, 0.995. And if you remember, the thing that I erased here, the probability of B2 is going to be the same. Okay, so let's write it here. The probability of B2 is going to be the same. So we have the probability of B1 and the probability of B2. Perfect. Okay, now I'm gonna clean this up a little bit. I don't need this anymore, so I may as well erase it. And now let's go back here, guys. We're not done with the problem. So the probability of the flight being safe is equal to the probability of B1 and B2. Okay, perfect. So once again, are these events independent? Is the probability of detecting the bomb 1 independent from the probability of detecting the bomb 2? Well, yes. Once again, we can assume independency, and therefore all we need to do is the multiplication of B1, of the probability of B1 and the probability of B2. So it's gonna be like this, and we have both of them, which is 0.995 times 0.995, and let's calculate such probability. We're gonna get a probability of 0.990025, and that's the probability that we were looking for, like that. So the probability of the flight being safe in this case, in other words, the probability of detecting both bombs by the dogs, will be 0.990025, and that settles the whole thing. So as you can see, guys, in this case we needed to interpret this event in terms of these two events, right? And then each of these two events, which I'm gonna square, each of these two events were interpreted in terms of the events D1 and D2. So you see, you have to sometimes do this type of detective work and reinterpretation in order to get the probability that you wanted in the first place. So that's it, guys. Thank you very much.